have more than 1,300 tests in our regression test suite. And it takes more than 7 hours to complete a full test run. And developers, they want feedback fast. They want to know if my code change breaks anything or if it's okay. And if you have to wait for a full workday before you know, then it kind of slows everything down a lot. And continuous integration is not possible if you have to wait for such a long time. It's not really continuous then. So no matter how small the change is, you have to run the full 7-hour test suite, even if it just affects a very minor part of all the tests that are available. And this is a big problem. So my mission statement for the thesis is to save time. And I thought you could save time by, after you submit a code change, you look at the code that was changed, and you use the previous regression test history to recommend a subset of recommended tests. So the solution is automated intelligent test selection. So by analyzing the data and the regression test database, you can build correlations between code packages and test packages. And these correlations can, as I said, be used to select only the relevant test instead of running all the tests. So how did I perform the test selection? I wrote a program that I called the difference engine. And it has two selection models that are called narrow and wide. The narrow model, it does, as I said before, it looks at which code packages were changed, and then it suggests that, yeah, you should run these tests, but you don't have to run the other ones. The wide selection model, it recommends all the tests that have a history of ever flipping. Well, a flip is when a test goes from pass to fail or fail to pass, because the code change that makes a test flip obviously affects the test somehow. And it works by going through these 4 steps: extract, parse, correlate, and recommend. The extraction phase is where the program talks to the regression test database. It extracts the results, but the results aren't really complete because we don't have information today about which tests or which code packages are changed for a regression test run. So I have to calculate it. And then there's also no information about which tests have changed their state from previous test runs. So I also have to calculate that. When that's done, I can build a correlation database where the changed code packages are correlated to the specific test that flipped. And in the end, you can use the program to get the recommended set of tests to run. And these are the results. This diagram shows how many tests you run when you run all the tests. The wide selection model runs fewer, about 400. And the narrow, it recommends on average 50 tests. It depends on the code package that you change, because some code packages affect a lot more tests than others. And it takes about 15 minutes to extract the data from the database, and the analysis and correlation phase is only 15 seconds. So yeah, it's faster. Because the full test suite takes 7 hours, and this would, if you run 50 tests, would take 20 minutes maybe. Of course, it looks good on paper, but I have to evaluate the results to make sure that the recommended tests actually find the possible regressions. And there wasn't time to test it in practice, so I did a theoretical evaluation. I did something that's called a k-fold cross-validation, and basically I used the available data to train my model, but I took part of it away to use as a test set to test my model against. And with k-fold cross-validation, you do this k times. This is an example of threefold cross-validation. So you split the data into 3 sets, use one set as a test set and the rest as training sets. And then you swap the test and training sets and repeat it 3 times in this case. I did, in the thesis, I did it 10 times. And then you analyze the results from the cross-validation, and you get metrics to measure whether the recommended set of tests could find the faults and if it was more effective. And this is what recall and precision are. Recall is the number of failed tests in a regression test run that were in the recommended set of tests. And precision is the number of recommended tests that actually failed for that test run. So if we look at the recall, running all tests, of course, you find all the faults because you run all tests. But the wide and narrow selection models aren't that far behind. The wide model finds 93% of the faulty the test that would fail, and the narrow finds 79%. But as you might know, a mean value, it's very sensitive to outliers, and sometimes there wasn't enough data to actually be able to recommend any tests. So you return 0 tests, and that will pull down the recall for the narrow model. Oh, I'm missing a slide here. Anyway, I was going to show the recall median, and the median values for all 3 of the models is 1. That is 100%. So it's actually better. The precision, on the other hand, is very low for running all the tests, because you run so many unnecessary tests, so the precision suffers. The narrow selection models is about 15 times better, so you waste a lot less time. So the question is, as I said in the beginning, I want to save time. How much time is saved? The narrow selection model will run less than 4% of the full test suite on average. That means that on average you will save more than 6 hours. And as median results that I couldn't show you would have shown, it's still very, you find most of the faults anyway. It's a trade-back, of course, but trade-off, but in many times it's actually worth it. The wide selection model, it will run a bit less than 40% of the full test suite and therefore save you 4 hours. And I would like you to stop and consider this for a while, because the wide selection model, it works by recommending all the tests that have ever failed. And this means that more than 60% of the tests in the test suite have never actually shown anything relevant, because they always pass. And since we all know time equals money, this is a very expensive insurance policy to run 1,300 tests every single time you submit a code change. Of course, there are some problems by doing this. First of all, turbulence. The calculations or the correlations are calculated from test flips. So if the code base is very stable, the regression test history never has any faults, I won't be able to calculate any correlations. This can be solved with automated mutation testing, though. That is, you knowingly introduce faults in your code to make tests fail, and then you can you have flips, and then you can provide the difference engine with flips that become correlations. Noise is another problem, because as time goes on, I will find false correlations that that are correlations that are due to random faults, for example, disk failing or network problems. These will cause tests to fail as well, and the code package will be correlated with the test, but erroneously. The solution to this would be to implement a way to forget old and rarely occurring correlations. Currently, my program doesn't support it. Last of all, starvation is a problem. You can't only run only the recommended tests. We have to run the full test suite regularly, for example, daily or nightly, to find new, to update the correlation database. Currently, I'm working on actually implementing this in practice into our, integrating it with our current continuous integration framework. And I want the process to be totally automated. So daily or nightly, you run the full regression test suite, extract the new data from the database, analyze it, and update the correlations with the new data. And then at the end, developers can choose to run only the set of recommended tests if they want to save time and have a faster feedback loop for continuous integration.